LNG is virtually the same as the natural gas you use in your home, with two important differences. LNG is a liquid, and it's cold. Very cold. 260 degrees Fahrenheit below zero, to be exact. The advantage of being in a liquid state is that it takes up less space. In fact, 620 cubic feet of regular natural gas, when cooled to a liquid, results in no more than 1 cubic foot of LNG. Cold LNG vapor is also heavier than air, but as it warms, it becomes lighter than air and rises. LNG is also environmentally friendly. In the event of a spill, it evaporates quickly. It leaves behind no residue and does not react chemically with the air. If spilled on water, it is not absorbed and does not harm sea life or affect water quality. And since 1964, LNG has maintained the best safety record of any fossil fuel. Unless trapped within a confined space, the burning will not create an overpressure or explosion, and LNG terminals do not create confined space. Another safety feature is that LNG by itself does not burn. The vapors will burn only when mixed with air, and then only with a lazy flame. A lazy flame means that LNG burns more like a candle than a blaze. This is different from other gas fuels such as propane and gasoline, which are highly flammable. As LNG mixes with more air, the mixture becomes too lean to burn. This is called a lower flammable limit.
Because very few places can keep it that cold. Liquefied natural gas, or LNG, is not readily available to most people.
LNG is natural gas in a liquid form. Natural gas is liquefied because doing so reduces its volume 600 times. That's like shrinking a beach ball into the size of a ping pong ball, so it's easier to store and ship long distances. LNG is very cold, but it is not corrosive. As Menine pours some LNG directly onto this cookie sheet, which is about room temperature right now, you can see the LNG quickly evaporating as it beads and slides along the pan. This is because the pan is so much warmer than the LNG. It's actually the same effect you get when you rinse a hot skillet with cold tap water in your kitchen. Ever wondered how cold minus 260 Fahrenheit or minus 160 Celsius is? It's far colder than most people can even imagine. Let's take a marshmallow. It will take no time to freeze when Menine dips it in the LNG. As you can hear, the marshmallow is now frozen. We're going to set it aside for now and come back to it in a few minutes when it's had a chance to thaw.
Some things become brittle when frozen in LNG. This lovely fresh-cut daisy will become stiff and brittle when Mariah dips it in LNG. As she crushes the flour, it breaks as though it was made out of glass. Because we are aware of this phenomena, special metals and materials are used to contain and handle LNG. Because we know LNG is non-toxic, we can dip a graham cracker into LNG. And after it thaws a bit, we can eat the cracker.
Cheers.
Cheers. All the LNG has evaporated off the cracker and it tastes great.
Very good.
Let's see what happens when LNG comes into contact with water. The LNG is so much lighter than water, it floats on the surface. Water is also warmer than LNG, so the LNG immediately warms and evaporates. Now you notice some ice crystals on top. That's just because of the really cold LNG temperatures. There is no residue left over. LNG has been shipped across the ocean for more than 50 years and has a very strong safety record. But in case of a spill on the water, no spill cleanup is required. So we can actually drink this very cold water.
Remember that marshmallow we stuck into the LNG? It was frozen then, and very hard. Well, guess what? It's returned to its original form. Oh, and the marshmallow itself? Back to normal.
LNG, which is simply natural gas that has been cooled to the point it becomes a liquid. It's the cleanest burning fossil fuel. Let us illustrate what that means. Mariah will hold this glass beaker over the candle, and watch what happens. You can see black carbon residues start to form. But if I do that over this natural gas candle, There's hardly any residue, as you can clearly see. LNG vapors will ignite only if the ignition source is more than 1,000 degrees Fahrenheit, or 500 degrees Celsius. That's pretty hot.
Yeah.
The cigarette that Mariah is holding burns at a temperature of around 700 to 800 degrees Fahrenheit, or 350 to 450 degrees Celsius, much lower than the temperature needed to ignite the natural gas, which is why she can pass the red-hot cigarette through the LNG vapors without even igniting it. In fact, Mariah can extinguish the cigarette in the LNG because there isn't enough oxygen in the container to keep the cigarette lit.
We've added some LNG to this flask. When the LNG evaporates, it returns to a gas. Maneen has attached a balloon to the LNG vapors coming off the LNG in the flask. Now let's convert that natural gas back into a liquid. As Maneen cools the gas with LNG, you see the balloon is contracting because the gas is cooling and becoming a liquid.
If you've enjoyed learning about the basic properties of LNG, as we've demonstrated, LNG is simply natural gas, the same natural gas that is used in homes all across the world, that has been cooled to the point that it becomes a liquid. In its liquid form, LNG does not burn. LNG vapors will burn when mixed with oxygen in a 5 to 15% ratio and combined with an ignition source of at least 1,000 degrees Fahrenheit, which is what makes the fuel valuable.
LNG is stored at minus 260 degrees Fahrenheit or minus 160 degrees Celsius to keep it in its liquid form. LNG has been used around the world for more than 50 years and has an impressive safety record. It really is a cool fuel.
Now we can begin to liquefy this clean gas. Many technologies can do that, but all are based on the same cyclic process that serves our kitchen refrigerators. That means we need some kind of refrigerant to remove heat from the gas so it'll condense into liquid. Here's how it works. First, the liquid refrigerant expands from a high pressure to a low pressure, turning it into a cold mixture of liquid and some vapor. Next, it passes through a heat exchanger that uses heat from the natural gas to turn the refrigerant into pure vapor. The natural gas is now a lot colder, and we can compress the refrigerant back to its high pressure. We cool the hot refrigerant in another heat exchanger until it condenses back into liquid. Then we expand the refrigerant again to repeat the cycle. The key to cooling and condensing natural gas into LNG is flashing the liquid refrigerant. And once the gas is LNG, we store it in tanks at very nearly atmospheric pressure. Liquid natural gas looks like water except that it boils off at room temperature. It's odorless, colorless, non-toxic, and virtually non-flammable. The cryogenic LNG stays in these storage tanks at a constant temperature between minus 159 and 162 Celsius. Evaporation helps keep it cool and liquid while it's stored on land or in the ship. We capture the vapors and either burn them for fuel or we recondense them and send them back to storage. Heat constantly flows from hot to cold all around us. Take the whooping crane. It stands hours on end in cold water. How does it warm its legs? Well, its legs serve as heat exchangers. Warm blood flows down its legs, heating the cold blood that flows back up. We call that a counterflow heat exchanger. Coil-wound heat exchangers have been around the longest. They evolved from 19th century locomotive boilers. Today, we wind multiple layers of tubes inside a pressure vessel shell. Natural gas and high-pressure refrigerant both cool as they flow up inside the tubes. Very cold refrigerant flows down around the tubes in the shell. Those wound tubes can provide a heating surface as great as 40,000 square meters. The other widely used LNG exchanger is the plate fin type. They're smaller and lighter than coil-wound exchangers, and we can easily scale them from small to large sizes. A look inside shows how it works. Fluids move through alternating layers of corrugated fins separated by flat plates, transferring heat between natural gas and refrigerants. Those fins enhance heat transfer from the fluid, and they conduct more heat directly into the plates. These layers of fins and plates can be combined in many configurations. We arrange the flows so as to optimize the heat transfer. The aluminum plates are brazed together. We attach headers to the stack to direct the streams of refrigerants and the natural gas. Then we install all this in a cold box. This heavily insulated box keeps everything cold. That gives operators more flexibility during steady and changing conditions. Plate fin exchangers transfer around 6 times as much heat in a given space as coil wound exchangers do. But coil wound exchangers can hold pressures all the way up to 250 times 1 atmosphere. And we can make them from different materials. And we finally achieve on a vast scale what that whooping crane's legs have long done in cold tidal waters. More than half of today's LNG comes from just 4 countries: Qatar, Indonesia, Australia, and Malaysia. But that's soon likely to shift. New natural gas discoveries promise to send Australia, the US, and Africa to the forefront.
The system includes the LNG tank, and on most heavy vehicles, there may be multiple tanks. Typically, LNG tanks are mounted on a truck's side rail, similarly to the way diesel tanks are mounted. In transit bus applications, they are usually found on the vehicle's roof. These highly insulated stainless steel tanks store LNG fuel. Multiple tanks are configured to operate in parallel. The operator doesn't have to fill them separately or select which tank is being used to fill the engine. Instead, the system has a single fuel fill connection and a single vent-to-station connection. Other components of the system include interconnecting tubing and hoses, a heat exchanger, sometimes called a vaporizer, and several fuel control devices such as the automatic fuel shutoff valve, overpressure regulator, and pressure control regulator. There's also a fuel gauge that displays the fuel level to the driver, and a low temperature light that warns the driver of abnormal system operation. Agility's standard LNG systems do not include a fuel pump. Instead, the tank pressure is used to feed fuel to the engine. No additional pressure boost is needed. When using blue fuel, however, Agility's optional cold fuel pressure builder is used to boost system pressure to provide the engine with adequate fuel. Even though the tank is very well insulated, a small amount of heat is always flowing into the tank from the outside, so pressure will gradually rise at a rate of approximately 10 to 15 psi per day, which is equivalent to about 3 to 5 degrees Fahrenheit per day. A series of regulators and valves manage the pressure in the tank so that it never exceeds 230 psi, and the pressure delivered to the engine never exceeds 150 psi. Let's begin with the tank itself. There are actually 2 tanks, one inside the other. The inner tank is wrapped with multiple layers of insulation, and the space between the tanks is vacuum sealed, much like a thermos. This cap on the outside of the tank is called the evacuation port cap and must be kept in place to prevent damage to the vacuum seal. Tanks are filled with LNG at the station through the fill receptacle. The LNG fuel fill receptacle is a pressurized connection and requires a positive lock with the station nozzle for fuel to flow. Agility LNG systems are designed to fill as quickly as possible, achieving a fill rate as fast or faster than conventional diesel fuel systems. The fill check valve prevents the tank contents from escaping in case of an accident or fill coupler failure. Note that if your vehicle has 2 or more LNG tanks, there will only be 1 fill receptacle and 1 vent connection back to the station. The tanks are connected and normally operate in parallel. Inside the main tank, a ullage tank is integrated to guard against overfilling and allow for fuel expansion and standby time. The pressure control regulator manages the flow of fuel from the tank when the vehicle is in operation. It supplies vapor when the tank pressure is above 120 psi, or liquid when the pressure is below 120 psi. As vapor is withdrawn from the tank, tank pressure is reduced. When liquid is withdrawn, pressure is maintained. Remember, as the tank warms over time, the tank pressure will slowly increase. By allowing vapor to be withdrawn from the tank, the pressure control regulator keeps tank pressure from getting too high. The inline check valve creates a small 2 psi back pressure when liquid fuel is being withdrawn. Restricting liquid flow this way helps the pressure control regulator work more effectively to rapidly reduce tank pressure. At the outlet of the tank, the excess flow valve protects against catastrophic failure downstream. The red-handled fuel shutoff valve on each tank allows the tank to be isolated for service, but is left open during operation. There's also a gray-handled vent valve. This allows excess vapor to be returned to the station during fueling and is otherwise normally closed. When liquid fuel is being drawn from the tank, a heat exchanger is used to vaporize it into the gaseous form required by the engine. The heat exchanger circulates hot coolant from the engine to warm the LNG. LNG systems have an automatic shutoff valve. Only when the key switch is turned on will fuel flow to the engine for operation. The pressure of the gas exiting the heat exchanger going to the engine is limited by the overpressure regulator not to exceed 150 psi. A capacitance liquid level sensor is located inside the tank as you see here. It sends a signal to an electronic control unit, which in turn drives the vehicle's OEM fuel level gauge. Each tank has its own mechanical gauge to indicate the pressure inside. Often there are 2 pressure gauges located at the rear of the tank. Note that these gauges only show the pressure, not the amount of LNG in the tank. The primary and secondary relief valves protect the tank from excess pressure. The primary valve activates at 230 psi and the escaping vapor is vented safely. The secondary valve is capped and activates at 350 psi. If you ever see the red secondary relief valve cap missing, you must consider the fuel system unsafe and take appropriate action as described in segment 7, pressure relief valves. Gas at between 100 and 150 psi at coolant temperature leaves the overpressure regulator and goes to the engine low pressure filter, which is not part of the agility system. When a driver parks his LNG tractor on Friday night and doesn't start it again until Monday morning, this is what happens. Tank pressure when the truck was parked equaled 120 psi, the pressure control regulator set point. The truck was parked for 2 days with a 15 psi pressure rise per day. By Monday morning, the tank showed 150 psi. Note, the tank did not reach 230 psi, so it did not vent. When the driver starts the engine Monday morning, since the tank pressure is above 120 psi, the pressure control regulator will be open, allowing vapor flow to the engine. As the engine runs, tank pressure will decrease until it reaches 120 psi. The pressure control regulator then closes, preventing vapor from entering the heat exchanger. The pressure control regulator will then keep the tank pressure at 120 psi until the engine is shut off again.